Okay.
I'd like to welcome you to Water Talk. Our speaker today is Dr. Richard A. Marston. Dr. Marston is an associate professor of geography at the University of Wyoming and has a joint appointment between the Department of Geography and Recreation and the Wyoming Water Research Center. Dr. Marston received his BA in 1974 from the University of California at Los Angeles, followed by an MS in 1976 and a PhD in 1980 from Oregon State University. Prior to joining the University of Wyoming, Dr. Marston was on the faculty of the University of Texas at El Paso. He's also conducted individual engineering and environmental consulting for government and private agencies. And Dr. Marston has received national awards for his water-related research. Some of these awards include the Association of American Geographers in Applied Geography in 1984, the Association of American Geographers Warren Nystrom Award in 1981, and he was also granted a Special Achievement Award in 1977 by the U.S. Environmental Protection Agency. Dr. Marston's major research expertise is in the process geomorphology, especially fluvial, and I can't pronounce this, aeolian, including environmental geomorphology, terrain analysis, and geological hydrology. That brings him today to our topic of geomorphic changes in the Snake River, Grand Teton, and Yellowstone National Parks. I'd like you to welcome Dr. Richard A. Marston.
All right. Thank you, Ari. Can we go ahead and have the slides and get the lights here? Okay. And Jeff, we can go ahead and turn off this overhead light if you'd like. And okay. Well, let me begin by acknowledging the financial support for this research that has been provided by the University of Wyoming National Park Service Research Center. This is a 3-year project, and we're just ending the first year. So what you're going to hear today is a bit of a preliminary report on our findings so far. Also, we've received support for the first year's funding from Chevron USA through their Casper office. That concerns the portion of the research that dealt with the effect of the 1988 Yellowstone fires. I'd also like to acknowledge the assistance on this project provided by my collaborators in crime here, Jim Schmidt from the Department of Earth Sciences at Montana State University, and Jack Schroeder, Chair and Professor of the Department of Geography at the University of Nebraska, Omaha, helped with the mass wasting portion of this work. Mike McFall with Laramie Soil Service here in town helped with the stream surveys. And in my own department, I've had some help from Dr. Bill Gribb and graduate students Dave Hare and Jack Mills. Well, I think we're all familiar with the Snake River in western Wyoming, and it's of course recognized for a large number of special resource values. For instance, the Greater Yellowstone Coordinating Committee has mapped major riparian zones along the Snake River above and below Jackson Lake. This is an area where you have extensive forested wetlands comprised of southern poplar, cottonwood, aspen. There's even some Colorado blue spruce on the floodplain, and of course willows, and this all combines to create some major wildlife values. For instance, the Snake River in this area is a major migration corridor and summer concentration area for elk, mule deer, antelope, and bison. One of the nice things you can do, you can take a raft trip down through this river, as I've done many times, is to occasionally see bison wallowing in the mud on their backs along the river, or maybe a moose on a mid-channel bar with its head down munching on some lily pads. It's also you also have streamside wintering habitat and nesting habitat for trumpeter swan and osprey and bald eagles. There are quite a few other important resource values of the Snake River. Here you're looking at a map of the northwestern quarter of the state of Wyoming, and the colors here designate streams of different trout stream classification as designated by the Wyoming Game and Fish Department. The Class 1 streams are shown here in blue. You can see this would be where Jackson Lake would be, and here's the Snake River running south through Jackson Hole. So the so-called blue ribbon streams, or Class 1 streams, are pretty limited in the state. There's just a few around. The yellow, orange, and red streams would be second, third, and fourth class streams. So a blue ribbon or Class 1 stream designates a reach of very high habitat quality containing significant trout populations of national importance. And this hasn't been lost on the fishermen and fisherwomen of the state. This is a view of the entire state of Wyoming now, and the dots here, red dots, correspond to visitor days for fishing. And I think you can see the concentration of activity again over here in Jackson Hole along the Snake River. You might be interested to know that the Jackson Chamber of Commerce estimates that somewhere between $25 and $30 million annually are added to the local economy in Jackson by fishing activity out there. And perhaps some of you have seen the old Milwaukee beer commercial where there are a couple of fishermen waiting in the middle of the Snake River claiming that life doesn't get any better than this. And it probably doesn't. There's yet other important values of the Snake River that are related to its geomorphic character. This perspective view of the state of Wyoming shows you a fence diagram corresponding to the 10-year, 7-day low flows in the state. So some index of low flows. And you can see by the time the Snake River leaves Wyoming and goes into Palisades Reservoir in Idaho, it has a significant volume of water even in extreme low flow conditions. So that's important for a number of in-stream uses and also withdrawal uses from that stretch of the Snake River. And that same water also contributes to recharge of the alluvial aquifers. So the height of pylons here corresponds to the mean annual recharge in acre-feet provided by rivers, and this is all due to the Snake River. Of course, this stretch is one of the premier sections of streams in the state for rafting and canoeing. So here again is another map of the state. This will appear in the Wyoming Water Atlas, as the others will. In this case, the red dots correspond to visitor days for rafting and canoeing. And you see a little bit down here on the North Platte and the Green River system, but no doubt that the best rafting and most popular rafting anyway is in the Snake River region. Well, rivers are dynamic features of the landscape whose characteristics vary over time and space according to changes in environmental controls. And my principal interest in life is as a fluvial geomorphologist, trying to understand why and how rivers adjust to changes in environmental controls. And the point I'd like to make here right off the bat is these resource values I've mentioned are tied to the geomorphic character of the Snake River. There's also some new concern about the operation and maintenance of levees along the Snake River downstream from Grand Teton National Park. I think some of the findings that we'll have here might bear on that question as well. But for the time being, I want to focus on the past and potential effects of two controls on the Snake River. The first of these would be the effects of Jackson Lake Dam. There was a lake, Jackson Lake, present before this dam was constructed in 1906. It was just a log crib dam at that time, and it washed out in 1910. The dam was replaced in 1916 by a larger dam that raised the lake level 39 feet. And you may be aware there have been some recent repairs, began, I believe, in 1984, and just finished at a cost of $76 million that hopefully ensure the dam is more safe against any sort of earthquake or seismic activity. The second major environmental control we want to explore and its effects on the Snake River would be the effects of the 1988 fires in the Snake River watershed. I think we're all aware that there was something like 1.4 million acres burned in the greater Yellowstone region in 1988, the most severe fire since the early 1700s. And a significant portion of the upper Snake River watershed was burned. Here's a map showing a portion of this. So you can see Jackson Lake here again for reference. Snake River has its headwaters up here, comes down like so. So you can see a good portion of the upper watershed in the above Jackson Lake, and also the Pacific Creek drainage, which comes up through here, were burned, and some of that area did experience very severe burning. So we're interested in the possible geomorphic effects of those burns either affecting runoff and or sediment supply to the river. Now, the objective of this study is to try to describe, explain, and predict changes in the geomorphology of the Snake River and related changes in floodplain vegetation. So as part of this, we need to separate the effects of Jackson Lake Dam and the effects of these 1988 fires from natural fluctuations that may occur in the Snake River. Fluctuations that may have occurred without those two controls. This is a complex problem, and part of the complexity is illustrated by this diagram, where you have time on the x-axis and some sort of control variable. You could think of it as either water, peak flows, or maybe sediment supply to the channel. And things are going along nicely until there's some disturbance, like a dam or a major fire. There's going to be a reaction time, a lag time, before the stream begins to adjust to this change. We want to try to identify that. Then there's going to be another period of time that geomorphologists call the relaxation time, nothing to do with spring break or anything like that. But that's the period of time over which the stream tries to adjust toward a new equilibrium. It may not happen. It may not reach a new equilibrium if another disturbance occurs at a frequency of shorter than the relaxation time. But if these major disturbances occur at a recurrence interval greater than the relaxation time, the stream can reach a new equilibrium and then will be maintained at that condition until, again, some new disturbance occurs. Now, there's also a lot of complexity involved just in the nature of the fluvial system. I don't really want you to memorize this diagram, except if you're a student in one of my classes, where we use this to introduce fluvial geomorphology. Really what you're looking at here in the boxes are either hydraulic variables or watershed variables, which interact in ways to produce just different types of channel geometry. We're trying to understand these interactions in the Snake River system. There's really never been a systematic study of the geomorphic character of the Snake River in Yellowstone and Grand Teton National Parks. Now, just to make sure we're familiar with the hydrography of this system, again, we're looking at this northwestern quarter of Wyoming. Here's Yellowstone Lake. This yellow boundary then is the boundary between the Snake River watershed and adjacent drainages. So the Snake River has its headwaters up here on Two Ocean Plateau, flows westward until it's joined by Lewis River, and then southward into Jackson Lake, and then it leaves Jackson Lake and flows generally southward through Grand Teton National Park. This would be the area below the park where the levees are located, and then down through this canyon where it's joined by the Hoback River and then flows westward into Idaho. Now I want to mention that as soon as the river leaves Wyoming, it enters Palisades Reservoir right over here, and that's going to play an important role in our interpretation of change on the river. Let's take a closer look now at the reach of the river beginning at the dam and going down to Moose. Most people here in the room are probably familiar with the Moose Bar, so you know the stretch of the river we're going to be looking at here. These are color infrared national high-altitude photography provided by the Department of Geology and Geophysics here on campus. So you can see we're starting here at Jackson Lake. Here's the dam, and the river flows in essentially a continuous pool for the first 4.3 miles. The water here is over 6 feet deep, substrate generally sandy, maybe some small gravel, and the gradient is very gentle. In fact, most rafting doesn't start until below this stretch because the gradient is so low. It's something like 2.3 feet per mile, very low gradient. We're going to talk about this cutoff right here. On the 1899 map of the river prepared by the U.S. Geological Survey, this cutoff did not appear, and the river went through this entire meander loop. This is known as the Oxbow now and is a very valuable area for wildlife habitat. Well, the next slide will pick up at about this point. The slides are always oriented with north to the top. So there we are up at the top. The river's coming along, and then here's the first major tributary which enters the Snake River below the dam. That's Pacific Creek. Again, a large portion of that drainage was burned. Pacific Creek supplies a significant amount of suspended sediment and bedload to the river. And in fact, since the dam operations changed in about 1957, the delta of the Pacific Creek has protruded into the river. The river continues then and is joined at this point by the Buffalo Fork of the Snake River. And again, a significant amount of sediment is added at that point. You can see that the channel, for the first time then, leaves a single channel and becomes braided as it moves down through here. You can see some old meander scrolls on the floodplain. And next summer, we're going to be mapping the vegetation between the dam and Moose and try to better understand the relationship between the channel shifts and the vegetation. Comes through this nice meander loop and moves on further down where Spread Creek enters the Snake River. This is a huge alluvial fan, actually covers this whole area here. And when you view this in stereo vision, you can see that the fan has moved the Snake River toward the west. Again, look at the old abandoned meanders over here, and the abundant supply of sediment added by the Spread Creek contributes to the formation of these point bars, mid-channel bars, for quite a stretch. So it's braided across this wide floodplain until you get to Dead Man's Bar. This is a deposit of gravel, that type of bar. And this is one of the popular put-in points for fishing and rafting access. So the channel at this point becomes much more steep. I should have mentioned the gradient increases also below Pacific Creek. It becomes about 4 times more steep, but still less than 1% gradient. And at this point, the gradient increases to about 16 feet per mile. So it's still much less than 1%. Very low sloping stream. The river is entrenched in the Snake River floodplain at this point, and notice how it's impinging against the glacial gravels here in the Snake River plain. A lot of bedload materials added at that point, but the channel is entrenched, so most of that material is moved on down. Here again is Dead Man's Bar. So the channel continues until this point where the floodplain widens out, get a little bit more meandering. Look at this fairly old stand of Colorado blue spruce. And then the final section, you go into this reach that people know as the maze, because it is quite difficult to find a good route through here when you're rafting. There are drownings each year when rafts get caught in logging, or not logging debris, but large woody debris in the stream. So the channel continues in a braided pattern until this point where it once again becomes a single channel, then Moose would be just off the bottom edge of this slide. All right. Well, the basic approach we're using in this study is to compile a sediment budget for the Snake River drainage above Moose. This means we want to quantify the movement of sediment through the drainage. The principal sources of sediment to the Snake River will be mass wasting and erosion from rain splash or overland flow, at least in the burned areas. That would be important. And the other source of sediment, as I've indicated, would be just channel processes themselves. Channel erosion by avulsion, the sudden shifting of a channel, or by shifts in pattern from a meandering to a braided form perhaps, or channel widening. So the usual approach when you do a sediment budget is to sort of follow a bookkeeping, accountant's philosophy, but we're also going to employ a geographic information system. We're going to map the sources of sediment to the Snake River, and we think we'll be able to better understand the shifts in the channel at any one given location by doing that. So we have these 5 research tasks here I want to go through. Controlled field experiments, the rainfall simulation on the burned areas. Then we'll talk about mapping from aerial photography and topographic maps to discern channel changes. We'll talk then about field-based surveys of hill slopes and streams. All 3 of these have been initiated this first year, and the number 1 has been completed. The 4th task will involve time series analyses of gauging station data. And then we'll talk about the geographic information system. This task number 5, we actually won't begin that until the 3rd year of the project when we've collected all the data from other sources. Let's look first then at the controlled field experiments. What we did here is examine runoff and soil loss on 70 hill slope plots. in the greater Yellowstone region. 23 of these were in the Lodgepole Creek drainage in the Shoshone National Forest, and 7 of these sites were in the Rockefeller Parkway between Grand Teton and Yellowstone National Parks. What we did here is used a rainfall simulator that was built for a previous project of mine. This simulator is a drop-forming rainfall simulator that applies 3 inches an hour to a plot. And you collect the water and soil that runs off the plot. This is what the plot looks after the rainfall simulator has been removed. This would be in one of the more intensely burned areas. And what you can see here is that after applying 3 inches of water over an hour, there was only about a millimeter of penetration of that water. See, it's dry right underneath the wet surface there. Now, this kind of rainfall intensity corresponds to about a 75-year event, rainfall event in this area. And you might say, well, why use such an intense event? Well, it really wasn't that intense because in July of last year, there was a thunderstorm in this watershed that produced runoff that was 9 times the estimated 500-year event. An enormous thunderstorm, and it produced tremendous changes in the Lodgepole Creek channel. This used to be a single channel with some good trout populations in there. My graduate student lived off of that for a couple of months. And after that event, this channel experienced a tremendous amount of aggradation and turned it into a braided channel. I should mention our sites were selected for the rainfall simulation on the basis of geology, slope gradient, and the logging history in the watersheds. So for each plot, you're looking at a plot almost the exact scale, 1:1. These are 2-foot by 2-foot plots. On each plot, we measured soil texture, percent organic matter, slope gradient, percent vegetation cover, percent litter cover, and then some variables related to the fire impacts, like the depth of the wetting front. How far down into the soil did the moisture penetrate from our experiments? We looked at the depth of soil charring and the presence or absence of water-repellent soils. Now, what we did is put all this data into the computer and did a stepwise multiple regression. And we were able to explain the amount of soil loss using the following variables: the percent litter, and whether the site had been logged or not before the fire, because this would affect the fuel load and the intensity of the burn on the plot. Also coming into play were the percent silt and the depth of soil wetting. We got an R-squared of 0.85 using these variables. I should point out that the rates of runoff and soil loss that we found in these burn areas were higher than anticipated by most of the early predictions that came out after the fires. For instance, on this plot, the runoff was 96% of the applied rainfall, most unusual amount. And we got soil loss figures up to 2.5 kilograms per square meter per hour. And this is the kind of soil loss rates you would expect perhaps for agricultural croplands. All right, let's move now to the second task. This was a lot of fun, mapping the channel from the dam to Moose using aerial photography and topographic maps. We were able to acquire either maps or aerial photos for a number of years, and what I've done is reproduced 4 of those maps for one short section of the Snake River for these 4 years, 1899, 1945, 1968, and 1983, just so you can get an idea of how the river has changed, at least in this one section, over that period of time. What's mapped as a solid color here is the permanently flooded riverine habitat as defined by the U.S. Fish and Wildlife Service mapping scheme. Now, when you examine these maps, basically starting with the one in 1899, moving to 1945, there's not an awful lot of change there, really. A little bit more meandering, but there's actually less braiding. You can see this braid up here near the top has disappeared completely. Just one single channel meandering through at that point. It's not an awful lot of change in that period of time. Remember, the dam was constructed in 1906. But then as you go to the more recent maps, you see an increase in the amount of braiding. And as I'll indicate later, this can be explained by a decline in the magnitude of peak flows being released by Jackson Lake Dam. Now, while you have lower peak flows, the trouble is that you still have these tributaries contributing large, coarse sediment. Pacific Creek, Buffalo Fork, and Spread Creek are adding bedload material to the channel. But no longer do you have those peak flows that are able to work that debris and maintain a single channel. Also, the channel bars, the mid-channel bars, are increasing in size and also in number over the last 50 years or so. And it's interesting that these same channel bars are becoming more stabilized by vegetation. The decline in peak flows, vegetation can gain a foothold in some of these channel bars. The other thing I'll point out later on is the flows in late summer are higher with the dam, and that keeps the water table higher and probably aids riparian vegetation trying to gain a foothold on these normally unstable deposits. Now, one other thing that our mapping revealed, again, I alluded to it earlier, was this cutoff right here, having been created after 1899. And what I suspect is it was the washout of the dam in 1910 that may have caused this cutoff to form. It wasn't present on the 1899 map. All right, the other thing we did with aerial photography and topographic maps was to look at the extent of mass wasting. And preliminary maps of mass wasting have already been compiled for this watershed by Jim Case of the Wyoming Geological Survey here on campus. So we benefited by his hard work already, and we were able to take those maps out into the field and visit the stream side, stream adjacent mass wasting like this one, and calculate the volume of sediment that had entered the Snake River and its tributaries from these events. Mass wasting is very extensive in this area. There are a number of shallow, rapid forms of mass wasting, like dry debris avalanches and wet debris flows. But there are also some very large and deep, slow types of mass wasting, like block slides and earth flows. So it's one thing to estimate the total volume that's entered the drainages from these mass wasting events, but we also are interested in the rate that this material entered the river. So Schmidt and Schroeder collected tree cores on all of these events and performed dendrochronology to estimate the rates of sediment entering the river. And we're talking about billions of cubic meters over maybe the last 100 years that have entered the river by these processes. Well, moving along, let's talk a little bit now about the field-based surveys of hill slopes and streams. The field-based surveys of hill slopes would be the mass wasting surveys I've already alluded to, and of course we did some stream surveys. When Schroeder and Schmidt walked the watershed, they tried to not only visit the stream-adjacent mass wasting, but also stratify their sampling by geology, slope gradient, and land cover, including burn intensity. And of the mass wasting sites that they visited, about 30% of them were in burned areas. Of the mass wasting that was in burn areas like this, about half of those mass wasting events became more unstable as a result of the 1988 fires. Which types of failures became more unstable? The shallow seeded mass wasting, because those are the ones that are going to be affected by the loss of vegetation. But a great amount of the mass wasting out there is very ancient and will not be affected by the fires. For one thing, if you've got unstable ground, you usually have aspen growing on it instead of the more fuel-rich conifers. Also, the broken topography that's created by mass wasting provides some sort of a natural fire break. All right. Well, the stream surveys are probably the most fun portion of this project for me anyway. And what this involved was making measurements between Jackson Lake Dam and Moose. We performed 2 separate stream surveys in this reach. The first one collected data on the reach type. In other words, is it a pool, glide, riffle, or rapid? The water depth, the bank fold depth, and an ocular estimate of the particle size distribution. The second survey that we did between the dam and Moose looked at 15 channel stability indicators. Now we're still reducing these data and putting them into a GIS format so we can understand, again, the spatial changes in these variables. But the other thing we want to do is return this next summer and collect the same sort of data upstream of Jackson Lake so that we can compare the trends as you move downstream in these variables, compare those trends above and below the lake. And we think that'll help us also understand the effects of the dam. All right, the fourth task that we were involved with would be time series analyses of gauging station data. There are some discharge gauging stations and also some sediment data that have been collected. The U.S. Geological Survey out of the Cheyenne District Office would be collecting some sediment data related to the fire impacts. But let's look at the discharge data for the Snake River just below the dam. And what you're looking at here is a residual mass curve of flow for the Snake River near Moran, the gauge just below the dam. A residual mass curve is used to show changing patterns of stream flow over time at one station. So what you're seeing here is when you have a positive slope to the curve, those would be periods when the flow is greater than the long-term average. And wherever the slope is negative, like right here, and certainly most of this section, those would be periods when the flow is lower than the long-term average. Remember, these are cumulative departures from the mean, beginning with water year 1904. And these are only summer flows that we're looking at. Okay, so what you can see is the effect of the dam being added in 1906, the washout, and then the reconstructed dam in 1916. And then after that, the amount of water released in the summer increased dramatically. That was the purpose of the dam, to supply irrigation water downstream. And here you see the effect of the regional drought in the Rockies and Great Plains during the 1930s. But then things picked up again until Palisades Reservoir was constructed downstream on the Snake River in 1957. Now what happened there is Palisades Reservoir became the primary storage facility for irrigators using Snake River water. And they didn't have to store so much water any longer in Jackson Lake. Instead, they could use Palisades Reservoir for that. And that meant that the hydrograph would be smoothed off in terms of the water coming out of Jackson Lake. So again, beginning with 1957, you get lower flows coming out during the summer. So that's a key date to keep in mind. Let's look at another analytical technique here. Constructed some synthetic hydrographs for the Snake River near Moran. Here you got your water year from October to September, and this is your mean daily discharge in each month. 4 different curves here. Let's look first at this period 1912 to 1956, before Palisades Reservoir. The symbol here, this dashed line for a virgin flow in that period, means the flow that would be occurring in the Snake River without the dam. So looking at this part of the hydrograph, you can see peaks in about June 1st and rapidly dropped off. Okay, that's what the virgin flow would be. But the flow for this same period with the dam, in other words, the actual flow, is illustrated by this solid line down here. You can see they had very low flows during the winter. In some years, the flow was actually 0 below the dam. And then you can see the rising limb of the hydrograph gets a later start, and your peak in that period occurred about July 1st. So there's about a 1-month delay there. But the peak itself, the magnitude of the peak, was not that different from what it would have been without the dam. So from this I conclude that the dam did not have a major effect on the channel up until about 1956. Let's see what happened after that. Looking at flows from 1957 to 1979, first the virgin flows with this dash symbol coming along about the same, rising and peaking, of course, June 1st. This is what it would be without the dam. Flows during this period were a little higher, but not dramatically. And so, the virgin flow hydrograph for that period is very similar to the first one. And I interpret this as meaning that climate change was not a major driving force in the geomorphic changes observed in the Snake River. But let's see what the dam did during this latter period. Look at this symbol now, this bolder version coming along here. And now you get the hydrograph sort of lopped off here in midsummer. And notice then that this time you have a major difference between the magnitude of peak flows in the Snake River. You're comparing this peak right here, what is that, about 6,000 CFS to something around 3,000. Cut it in half. And so now the decline in magnitude of peak flows is going to have a significant effect, I believe, on the channel, beginning with the opening of Palisades reservoirs. The reservoir far downstream from the study area affects the operation of Jackson Lake. All right, well, what can we say in the way of preliminary conclusions then? I'm going to say that the Snake River channel was fairly stable up until about 1957. You still had high peak flows and a high supply of coarse sediment supplied by these tributaries below the dam. There was a slight increase in meandering up till this period of time, but not an increase in braiding. You expect an increase in braiding when you get large volumes of large-sized material added, while at the same time peak flows decline. But since 1957, there are now new, larger channel deposits of coarse sediment from these sources I just mentioned. You can see these in the unvegetated deltas of the tributaries coming into Snake River. You can see these deposits as point bars in some cases, and also as mid-channel bars leading to more braiding. The other thing then that's happened over this period of time is that vegetation has encroached on these mid-channel bars. Again, because of the lower peak flows and the higher late summer flows keeping that water table up. This has served to stabilize the mid-channel bars and preserve the braiding pattern. Once the braids have been established and then revegetated, they seem to be pretty stable. We're going to try to confirm this observation with our floodplain vegetation mapping this coming summer. Now, what about the 1988 fires? On the one hand, they did accelerate rain splash, sheet wash, rill erosion, and gully erosion on hill slopes. But the sediment coming from these processes into the Snake River system is a fairly small size. So it's going to have a short residence time, be flushed out, and not have any major effects on channel morphology. Now, on the other hand, the fires may accelerate some forms of mass wasting, the rapid shallow forms, which will introduce larger size material. When we work in the stream next summer, in the upper part of the watershed, we'll look very closely at the effects of this mass wasting on the channel sediments. I think by continuing this study for another 2 years, we'll be able to complete a reliable sediment budget in a format of not just bookkeeping, but also a geographical information system. And this will provide us with a tool to explain the past changes and maybe even predict future changes in the Snake River channel. And ultimately, I hope we can overcome the problems facing this fluvial geomorphologist as he ponders the fluvial system up here, and most of his work here is in the theory box, and what we're trying to do over the next 2 years is move some of this over into the proof box. Thank you very much. be glad to take any questions. I know you just wanted to find out where the fish were in the river.
I have a question for
Yeah,
you.
Bob. Yeah.
I want to put your what red button? I can find a red button.
Next to the microphone there.
Oh. Okay, I want you to put on your fishery biologist hat now, in addition to your fluvial geomorphologist hat. And what's that mean for the fish in the Snake River? All those changes, the different hydrographs and the cutting the hats off and that sort of thing.
Well, initially I think when the braiding increases, that would not necessarily be a good thing for the fish, because you get the same flow going through multiple channels of very coarse debris, and the depth of the water is not as ideal as it might otherwise be. The particle sizes might be too coarse for the development of pool riffle sequences and any kind of spawning situation. But now, as vegetation moves in and sort of stabilizes the situation, I think you're going to see less flow spread out in these braids, and the braids themselves will become more narrow. We're starting to see that with the aerial photography. And then you get the same amount of water in a more confined braid, more scouring, deeper water, and I think it'd be probably pretty ideal for fish. And from what I'm aware of regarding trout surveys in this river, it's still a pretty ideal situation. So now what happens downstream with the management of these levees might be a different question. But that's my impressions as a non-fisheries biologist and a very poor fisherman besides. But I tell you what, when we were doing these stream surveys, you're constantly looking in the water at the sediment and so on, recording particle sizes. About once a minute you'd see a big cutthroat floating right underneath you, and sort of distract you for a moment, I have to admit. But there are a lot of fishing. Well, yeah. The ones I never get, yeah. Jack, yeah.
In the Casper Tribune, I've been reading that the state or BLM is trying to swap some water rights in Palisade to transfer those water rights upstream. Is that correct?
That's right. And the idea there, as I understand it, is the state would use water rights they now have for in Palisades Reservoir, the water that's stored in Palisades Reservoir. They would keep that in Jackson Lake and release it during periods of low flow, which are in the winter. And am I right on this, Bob? And so you saw the shape of the hydrograph with and without the dam and how low those flows can be in the winter months. So the idea is to maintain a little bit more flow at that time of year. Yeah, Dave.
Last year, in August, there were some severe thunderstorms in Yellowstone, and I and my students were caught in some mudslides that resulted from those mudslides. I'm curious, based on your work with this rainfall simulator on the burnt areas, what impact have fires had on increased mudslide activity, or is this more related to these large catastrophic storms
Yeah.
that you mentioned?
I think there were some major thunderstorms last summer that were very local in their limit, in their extent. I mean, in some cases 4 inches in an hour and this kind of thing. And there was, in one case, a car that was washed into the Snake River as they passed through an area where a mud flow was occurring. So these things were occurring, especially in the volcanic terrain, not so much in the glacial sediments. But most of this seemed to be occurring in the Gibbon River watershed, north of the Snake River watershed. Yeah, okay, unfortunately. But Schmidt and Schroeder, my two colleagues here, working only in the Snake River drainage, reported to me that they saw very little evidence of accelerated, rapid, shallow forms of mass wasting, only an increased threat of it. But now the interesting thing will be to see how much revegetation occurs on these unstable slopes. And when we go back next summer, there may be a lag effect, and you'll start to see the effects of that in the stream. So, based on what they've told me, they didn't see much of an effect in the Snake River watershed, although we are aware of these other areas. But next summer when we walk the river itself from the head of Jackson Lake upstream, that's when we'll have a better idea on the stream impacts of mass wasting, which they haven't looked at yet. Okay, yeah.
Lodgepole Creek is in the highly erosive Absaroka volcanics too. What sort of control areas did you use for your rainfall experiments?
Right, and this area, in case it wasn't clear, is not in the Snake River watershed. But the reason we chose it is because Henry Shovik, the soil scientist up there with Yellowstone National Park, said this was the area that had the most severe burns. So we knew we could get a worst-case scenario if we went into that area. And the Lodgepole Creek watershed itself is stratified geologically into two major types. The upper part of the watershed is in the Absaroka volcanics, very highly erosive, tremendous amounts of mass wasting, real gully erosion were observed there. So we did take some samples there, and we also had some control sites on the volcanics. But then also went into the lower part of the watershed, which is covered primarily by glacial sediments, and again had a range of burn conditions and controls there. So in the control plots, normally in a forested situation, you don't expect to find any runoff or soil loss. We did find runoff and soil loss, a small amount, because there are water-repellent soils even in these unburned areas, probably related to the drought and its effect. But certainly when an area was burned, and especially if it was logged and the logging slash was still on the ground when it burned, then you have tremendous rates of soil loss and runoff. Very little water penetrating into the soil. So yeah, the worst case scenario would be up in the Absaroka volcanics on a steep slope where you had logging and a severe burn. And then you get these very high rates of erosion. Is that it? All right. Well, thanks a lot.